permutation since I had to do more work. So yeah, when Ailey and I were planning this day, we decided it would be great if she could concentrate on simple groups and tell you the stuff that's known about generation about simple groups, and then we would let Scott talk about Scott's marvellous results, and then I would try and tell you a bit about just the general picture of generation of finite groups. And I'm going to talk a bit about minimal generation, a little bit about random generation, and then about some other things as well. So, general things. So throughout here, I'm going to have G will be finite, and we've seen this notation loads, but just in case, dg is going to be the minimal number of generators for G. And then, well, what can we say in general about D of G? So if you were going to try and do something with no further information, you might think, well, order of the group, maybe I need to know something, obviously, to give you an answer to that. And so if you think about doing it by group order, well, I might have a vector space over GF2, and so I just have to pick something that generates some subgroup, the next thing generates a subgroup that's at least twice as big, the next thing generates something that's at least twice as big again. So certainly we can always say that D of G is less than or equal to the logarithm of the order of G, and for me, log is always going to mean log to the base 2. And in fact, that bound is tight because I just gave you the example as we talked through it. So order is not very helpful, because conversely, the monster is 2 generated, and it's quite a lot bigger than order 4. So order isn't very good, so I need to give you some other more useful bit of information about the group to make sense of asking questions about DG. So very much coming into today's theme, let's start by thinking about minimal generation for subgroups G of the symmetric group Sn. So imagine that the information that I give you is that G is a permutation group on n points. Well, there's an example we've seen in at least 2 talks already, I think Veronica really showed us this, and possibly Gareth showed us this as well. Let's temporarily assume that n is even. It's almost identical if n is odd. And let's consider the subgroup G generated by 1, 2, 3, 4, 5, 6, up to n-1 n, just disjoint 2 cycles. And if n is odd, then put some fixed point on at the end so that that makes sense, which is why I said n even. Well, that's my elementary abelian 2 group back there again. So in this case, D of G, even if we drop the n even, I'm just going to get the floor of n over 2. So that's quite a big number, but okay, that is our example. And then, can anyone think of an example on 3 points that does worse than 1.5 generators? On 3 points. Everyone's being too nervous to speak on the last day. Well, if you think of the symmetric group on 3 points, it's not cyclic. So it needs at least 2 generators. So that's a little bit worse than 3 on 2, rounded down. Well, there's a theorem going back to, I think she was called Annabelle McIver and Peter Neumann. Now, this is a bit awkward if you're trying to trace this down. It's stated in a paper of theirs from '87, but the proof actually appears in a paper by Peter Cameron, Ron Solomon, and Alexandra Terrell, where they're doing something else, and they just attribute it to Neumann. And they prove in there that if G is contained in Sn, because that's our assumption for this whole section, then D of G is less than or equal to the maximum of n over 2 and 2. So those 2 examples I just gave you are the 2 extremal examples, and otherwise you don't do any worse than that. Well, I came at this from a computational group theory thing where I was interested in finding small generating sets. And so Munsey, I think, amongst other people, has mentioned that you can always get a quadratic size, Mason-strong generating set. This tells you that you can always find a linear size set, but we'd quite like to do better than that. And clearly we're not going to do better than that in general, because I've given you these examples. But can we do better than that by using some of the theory that we have seen multiple times this week? And let's jump all the way from 1987 to Gareth at the back there last year, 2021. I think he's at the back there. Yes, he's at the back there. Who proved that if G is transitive, then we can do a bit better. In particular, D of G is at most, and I hope I've got my brackets the right way around here, the square root of 3n over 2 root log n. So the constant is the square root of 3 divided by 2. And, well, we're not looking like n over 2. We're not looking like a constant multiple of n. We're looking like a multiple of n over that enormously large term, the square root of the logarithm of n. That's quite a small correction factor, but it is a correction factor. Now, there's an infinite family of examples that I won't put up because they're a bit nastier, that shows that asymptotically, you're not going to be able to do better than something looking a bit like this. So the family of examples isn't quite this shape. It's something over log n plus a log n term. So it might be that there's no really neat way to get a single number to put here, because that's not quite the right shape, but this should be the leading term, and the second term is going to be a log n-ish type thing. Okay, well that's better, n over root log n. That's not much better, right? And we've seen this week that primitive groups are really, really special. So here's somebody who could be in every single section of almost every single talk I give, Andrea Lucchini, together in this case with Menegazzo and Martin Ricci in 2001. So this is an asymptotic result. It says there exists an absolute constant C such that if G is primitive, then the minimal number of generators for G is at most C times, this is looking like n over the square root of log n, we suddenly get all the way down to log n over, critical correction factor here, I laughed at that being small, the correction factor here is the square root of log n. Which does grow, but grows, I mean, I tried computing some values of the square root of log n. It takes a long time before that number reaches 2, let's say. But it is an increasing function, so small correction. We don't know what C is. I think this is one where you can get some sort of bound on C by staring at the paper, but it's by no means correct. Gareth is thinking about it, but there is nothing ready for public consumption yet. But anyway, there is a C, and C is not that big, so C is going to be less than 10, I think. I just can't remember exactly what the numbers are. We're not looking at like a huge tower of exponentials. How close might this be to being correct? Well, I don't have good families of examples here, but let me show you something that's almost a primitive group that we've seen, again, in various talks this week. So, consider AGL, the affine general linear group, in dimension m over GF2. That's a nice primitive group, and that's sitting inside the symmetric group on 2 to the n points. Now that can be generated with just 2 elements. That's not the one I'm caring about here. It's got a normal subgroup. It's got an abelian normal subgroup, a regular abelian normal subgroup, which we call V, typically, which looks like a little copy of the vector space there. Now, V is not primitive, but it is a normal subgroup of a primitive group. And, well, this is looking like I can only count generators of vector spaces, which is almost true, but not quite. But I can count generators of vector spaces. And that definitely needs n generators, and you can't do any less than that. So here, D of V, which is m, is precisely log of my degree there, 2 to the m. So you're certainly not going to do any better than log n for quite a wide class of things. So this can't be that far off being tight, because this is not very far from being all of that. But I can make my vague, not very far offs a bit more precise there. So Derek Holt and I, ages ago now, old, back in 2013, proves that if G is a subnormal subgroup of a primitive group, then the minimal number of generators of G is at most log n. So we see that example here. So if I can find a primitive group and then take normal subgroup, normal subgroup, normal subgroup, anywhere I stop down that chain, I'm never going to need more than log n generators. And kind of your intuition here ought to be, in primitive groups, we've got this Reith product. We've seen lovely descriptions of the base groups of Reith products. And base groups of Reith products look a lot like the groups that Muncie was talking about, computing normalizers, and they have quite a lot of generators. So if you have an imprimitive group, you can usually find some normal subgroups with quite a lot of generators, whereas once you're in primitive land, no, you can't. So you can drop down to normal subgroups for as long as you like, and you'll never need too many generators. That's enough, I think, now for permutation groups. Let me tell you a little bit about generation of matrix groups. So, section 2, I'm still on minimal generation, so I'm still talking about D of G, and I'm going to talk about G being subgroup of GLDF, and at least half my D's are going to turn into N's. I will try and keep the D's being D's, but if I write a D, tell me, because it should, if I write an N, tell me, because it should probably be a D. Now here, I'm interested in finite groups G, but F can be infinite. So most of the results in here are going to work for arbitrary fields. The first one, though, isn't. So just as I started here by giving you a bad example in some sense, let me start by giving you a bad example. I'll give you a bad example over a finite field. So let's consider the group G, 2 by 2, looking like a whole collection of transactions. 1A, 0, 1, where A is in some finite field of order P to the E. This is isomorphic to a vector space. I can count generator numbers of vector spaces very easily, so I know how many generators you need for this thing. So this is isomorphic to Fp to the E under addition, and so the minimal number of generators here is E. Well, that's not great because I'm obviously featuring the exponent in the field, but you can pump this example up very badly. So I won't write down the details, but if you take ones down the diagonal and then a square d over 2 by d over 2 block, which can have any kind of nonsense you like in that top right corner, then this looks like a vector space over my field F of dimension d squared on 4, and so we're looking like d squared on 4 generators there. So if this is my G, then this tells me that d of G is d squared on 4 times E. So that's nasty, because I started by saying d of G is something close to, it is certainly no more than log of the group order, and the order of GL is no more than q to the d squared, so d squared log q is log of GL, and that's looking really worryingly close to d squared log q. So that's saying if we don't put some restrictions on, I mean, this was at least a fair bit smaller than log of n factorial. There's a whole log n term missing, but this is really not much smaller than log of the order of GL. So we clearly need to define our way out of the problem and find some nicer groups to draw. And one way in which that's completely justified is Clifford's theorem tells us that these things, for example, don't hold up as normal subgroups of various nice groups. So let's think about various nice groups. Somehow this definition hasn't appeared this week, I don't think. G is completely reducible. I mean, I think it's appeared in some talks, but I don't know if we've had the definition written down. So G is completely reducible.
Reducible?
Completely reducible, thank you. If, I didn't even write all the letters reducible, did I? I kind of moved some of them forward and turned the C into an R. Oh, there we go, reducible. If F to the D, my vector space in which we're acting, is isomorphic as a G module to some direct sum. V1 plus, I don't care, VC, let's say, where each VI is G. So if you are having difficulty absorbing that definition, most of the places I'm going to use it, you can think of the fact that an irreducible group in particular is completely reducible with c equals 1, but some extra things are completely reducible as well. So you can think of your group, if you can put it into like block diagonal format, where you've got a diagonal block acting on V1, and then you've got another square block acting on V2, and another one like this. So this is a nice class of groups that's more general than irreducible, but still has a lot of the same properties as irreducible groups. Well, let's make an example. So if I'm going to call it I wouldn't normally use that for something, but I want this to be a fourth root of unity in F. So it seems reasonable to call it I just temporarily. And then we actually saw this representation yesterday, and John's gone, but I need to spend very little time convincing you that the group generated by north minus I is a little copy of the Quaternion group of order 8, and I can make it exactly when there's an I floating around there. And then if we look at the group generated by the scalar I times the identity matrix and Q8, so I times the identity matrix would be a central element of order 4, which there isn't in Q8, so this gives us an extra bit of 2. Well, there's a 2 cubed quotient of that thing, an elementary abelian 2 cubed group sitting on top, and I have to generate that elementary abelian 2 group. So you need 3 generators for that thing. And I could then make a whole load of copies of this and make a completely reducible group with just like Q8, direct product Q8, direct product Q8, direct product Q8. So that gives me 3 for each 2-dimensional bit. And Isaacs, back in 72, proved that if G is a completely reducible finite, I want to say P group, but it sounds too much like I'm talking about the characteristics, so let me just say finite R group. We're making no assumptions on the field here. Then in fact, the minimal number of generators of G is less than or equal to 3D on 2, which is exactly the number that you would get from copying this one.
Here your field could be anybody of characteristic different from 2, right? In your example.
Well, you need a fourth root of unity, so I can't do it in
different from 2. Ah, right, and 3 as well.
On net fields, I need a fourth root of unity, which I don't always have. So yes, I can't do it in characteristic 2, and I can't do it if Q's congruent to 3 mod 4. So Isaacs proved this, which is lovely, and then completely independently of each other, but in the same year, Bob Goralnik in 89, and separately, here's Andrea's appearance in this section, in 89, proved that if G is finite, and if for all CELO subgroups S of G, the minimal number of generators of S is less than or equal to some number T, say, then the minimal number of generators of G is less than or equal to T plus 1. So this is a completely general statement. If you can find an upper bound on the generator number of every single CELO subgroup, so just find the worst one, then you can generate the whole group with only one more generator than that. Well, there's an obvious consequence here, but in fact it took quite a lot more work for Kovacs and Robinson to show in 91. So 2 years later, and they do talk about this, but it takes a bit more work than you might think to show that if G is finite and completely reducible, then in fact D of G is less than 3D on 2. So they got rid of the plus 1. I love these results because they're completely independent of the field size. Right, the field doesn't pop up in any of them. Except that, so I'm not going to write this up, but Derek and I sometime later essentially prove that this fourth root of unity is a unique obstruction here. So if you assume that your field has no fourth root of unity, then you can turn that 3 over 2 into a 1. So somehow, this isn't the only bad example, but having a fourth root of unity is the only way to get a bad example, which is remarkably similar to John's talk yesterday, where Q8 was somehow an obstruction. Right. But completely reducible, I said you can think of it as being like irreducible, but it's not the same as irreducible. So let's give Andrea a second appearance in this section. It's hard to squeeze him out. So, same authors, I think it's a different paper, but it's the same authors, Lucchini, Menegazzo and Marigi. It's a different year, 00 this time. 00 showed that there exists, I'll phrase it in functional format because I prefer that actually, C from the naturals to the reals such that if G is irreducible, then the minimal number of generators of G is at most this function of D times D over root log D, and this C of D, I mean they phrase it as a constant, and the idea is that C of D grows slowly. Sorry, do I mean C of D, Gareth, or C of F?
I think it's C of F.
I think C of F, don't I? Sorry, yeah. Fields. Sorry, I was just writing that up and thinking that doesn't sound right. So it's a function of the field. So the overall growth rate looks like D over root log D, but a bit like there was some fudging here, depending on whether Q was 3 mod 4 or 1 mod 4 or not, you can get a bit of a fudge here. We don't know what those are yet, but Gareth does. He just hasn't published yet. So there is a final answer here, but it's not quite ready for us to see yet. Right, so irreducible.
And G is finite.
Yeah, G's always has to be finite here, sorry, yeah.
The field is not necessarily.
Field, well here it's a function of the field, so they're not quite as precise as all that. I mean if G's finite then you can realise it over.
They have a similar result for number fields.
Yeah.
Finite.
Yeah. Yeah, so the field has quite a lot of freedom here, but the group has to be finite. Well, just like the permutation groups, where being intransitive meant you could need quite a lot of generators, and I was talking in whiffly ways about how in primitive groups, in this Reed product, you've got this base group, which might need quite a lot of generators. For linear groups, you've got your reducible groups, C1, which correspond to the intransitive groups. And then you've got your C2 groups, the imprimitive linear groups, which correspond to the imprimitive permutation groups, and they again sit inside Reed products. So what happens if we somehow try and get ourselves out of those? Right, here's a horrible looking definition. I'll write it up and then I'll talk to you about how to think about it. G is weakly quasi-primitive. You can think of this as a wide generalization of primitive. It's another generalization of primitive, but it's a generalization of primitive in the context of linear groups, not permutation groups. We've seen also generalizations of primitive for perm groups. So what is this generalization? If every characteristic subgroup of G acts, you sort of think I'm going to say irreducibly or something, but I'm not going to say that because there's these C4 groups, right? So when I was going through what happens if you've got a reducible normal subgroup, I also said that there were these tensor product groups where your normal subgroup is reducible, and when you split up the vector space, you're acting in the same way. Each direct factor is isomorphic. That's called acting homogeneously. So I'm going to say if every characteristic subgroup of G acts homogeneously. So, if you don't like being that vague, all primitive linear groups are weakly quasi-primitive. Obviously, the definition would be a horrible one if that wasn't true. But we're also catching some in primitive groups as well, because we're only looking at characteristic subgroups, we're not looking at normal subgroups. And yeah, we've just got this homogeneous construction. Let me give you an example. I'll give you an example from something I didn't do in my first lecture. So in my first lecture, let me write this down here, there were these C6 groups that I just really rubbishly wrote a couple of arrows, having started with, I've got a minimal normal subgroup whose scalar quotient looks like a direct product of cyclic groups of prime order. Well, in general, the largest you're going to find in there looks like a central product of a cyclic group of order 4 that's being scalars. Here's my R group. It's got order 2 to the 1 plus 2m in this particular case. I want 2 in this case. And then I can put a symplectic group on top, preserving the natural form on that extra special P group. So that's a C6 group. And it will sit inside GL 2 to the m Q for various values of Q. And it's got a very obvious normal subgroup, which looks like 2 to the 1 plus 2m. So this was my group N that I was kind of waving my hands about in lecture 1. This is my minimal normal subgroup. And it's acting irreducibly. Well, quotient out by the centre and you get a vector space, and I can count generate a number of vector spaces. So if I take this normal subgroup as my group G, then I need 2m generators for it. And this is definitely a weakly quasi-primitive group. This is a primitive group even. So sitting inside here, I've got the minimal generator number of this group G is 2m, and what's my dimension? It's 2 to the m, so that's twice log d.
Excuse me, can you just say again what R was? Because before it was A prime, but not necessarily the characteristic.
Oh, sorry, that should be 2. Sorry, I was changing my mind about how to write this. Sorry, that should be 2. Sorry, apologies. Thank you, that was an excellent question. Sorry. Yeah, SP2M2 is, so this you can think of as a formed space with a symplectic form on it, and you put a symplectic group acting with automorphisms on your formed space. So minimal generator number there is 2m, and in fact, Derek and I proved, again in this same paper in 2013, that if G is a subnormal subgroup of a weakly quasi-primitive group, then the minimal generator number of G. No, let me do this right. GZ over Z. So Z is the scalars of the whole thing. So throw in all the scalars and then quotient them out. Otherwise, you sometimes have to put a +1 in, which you don't want to do because the proof is inductive, and so you don't want +1 appearing ever. So the minimal generator number of GZ over Z is at most 2D. And we don't know much if you actually say primitive, rather than... So we do know what happens if you delete the subnormal subgroup bit. The 2 turns into something slightly more smaller than 2, but the constant stays. I mean, the fact that it's log d changes stays the same. I suspect if you actually go as far as primitive, you can maybe divide by square root of log d or something like that. Should be what it looks like by analogy, but I don't know. Maybe Gareth does. Right. That's all I'm going to tell you about minimal generation, but I'd like you to remember that the overall theme is that in general, if I just say we're inside SN or GLD, then the bounds can be pretty big. They can be basically almost as bad as what you get by taking just log of the biggest group order. But as soon as we start putting nice conditions on, then you win and win and win. Let me give you a short discussion about how to turn this round to random generation. And there are lots and lots of ways you could turn this round to random generation, and I'm only going to tell you about one of them, because I'm trying to do all the generation of finite groups in 50 minutes, so we'll just do one. So this is where I came in from, actually. So to do with the stuff that Elise was talking about, quite often when you're working with a group on a computer, you have some way to spit out elements of a kernel of some action. You find that 2 things turn something to the same place, and so smash one with the inverse, and now you're fixing stuff. You've got an element of the kernel. So you can produce normal elements of some normal subgroup but you don't yet know what group you're working with, and you certainly don't know what the normal subgroup you're working with is yet. And the question is, when can I stop making them? When do I know I probably have generators for this normal subgroup? Okay, can I stop once I've made 6? I think Charles once had a sort of universal constant of 10 works for most matrix groups as a kind of rule of thumb. But yeah, what can I prove about when I'm done? When can I stop and now start assuming that I've probably got the normal subgroup generated and I can start looking at it? So let's give a useful definition in this context, which is to say fix an epsilon, oops, white, somewhere between 0 and 1, neither the one nor the other, and let's define, so this is a bit like a minimal generation, but it's a probabilistic generation, the epsilon of G to be the number of random elements required to generate G, but you don't know precisely what you want is to bound the failure probability. So if we want to use this in Monte Carlo algorithms, so I want an explicit bound on the failure probability. So it's allowed to not generate G with failure probability at most epsilon. So say I want my algorithm to work with probability at least 1 minus 1 over 2 to the 10. How many random elements do I need so that the failure probability is at most 1 over 2 to the 10? So by random, I, as ever, mean uniform, independent, all of those nice things. Yes, I'm safe for this one. Well, Lubotsky, and I'll give, if time at the end, some motivation for why he proved this, but he proved a marvellous result, and he proved it for one particular value of epsilon, but he only didn't state it in general because he was hunting an application. So let me state what he could very easily have stated. You won't find this in his paper, but if you look at his proof, this is what, and I'm spelling Lubotsky wrong. Is that better? In 2002. He proved, okay, what ingredients do I want? I want G to be finite. I want T to be, I want epsilon to be in 0, 1, because that's going to be my failure probability. I want G to be finite. I want T to be such that when I stick it into the Riemann zeta function, Euler's zeta function, because we're talking real numbers here, I get something at most 2 minus epsilon. So the Riemann zeta function decreases as epsilon gets bigger. So as I want this to get closer and closer to 2, I need T to get, sorry, as I want this to get further from T, because I want to shrink my from 2, because I want to shrink my closer to 2, because I'm shrinking my failure probability means that T gets bigger. Sorry, let me get that the right way around. Then the number of generators you need from G to generate it with failure probability at most epsilon is at most, well, you certainly need the minimum number of generators of G. You're not going to get very far without them. And then he shows that you can take log of the order of G. So log G was our original upper bound, but this is log of that, so that's quite a lot fewer, plus 2 plus T. And so I'm not going to write up the consequences, but it means that for every one of these, and one of those versions of direction has to prove ours in the form of what you get for a normal subgroup, you have an upper bound here on how big G can be. It can't be any bigger than GLDQ, which means log of the group order can't be more than D log Q, which means that log of the group order can't be more than log D plus log Q. And so the number you need to generate it with failure probability, whatever, is 3 log D plus log Q plus 2 plus T. And so that just immediately turns all of these minimal generation results into random generation results. I'm going to say a little bit more about random stuff at the end, but I thought I would keep that section very short and sweet because it's a lovely theorem. Okay, I think I've got time to do at least some of this. Okay, I'm going to talk now about a different kind of generation just because I've been working on it recently and got kind of excited about it, so let me tell you about it. So I'm going to talk now about independent generating sets, just very briefly. Mostly to say, I was worried that this earlier section somehow looks like everything's done. So here's a section where loads is not done. I don't want to make you feel like generation questions are dead, because they're very much not. So there's been various different names for these. I'm going to go with Andrea's for now. I was going to go for minimum versus minimal, but that's going to get lost on the board. So let's go for independent. X is an independent generating set for G if two conditions. Firstly, the obvious one, it had better be a generating set for G, otherwise I'm talking nonsense. And secondly, if I take anything away, I no longer generate G. So my favourite examples of these is obviously a basis for a vector space is an independent generating set for that vector space, because it generates, and if you take anything out, you don't generate anymore. So there's an obvious question, what do these look like? So let's define a group invariant, M of G, to be the maximum of the size of X, such that X is an independent generating set. Very little is known. So it's a really interesting question with lots and lots of applications. I'm going to mention just a couple of things. Firstly, a friend of mine from PhD years who died very young, and so I keep wanting to advertise his PhD work. He was a PhD student of Jan Saxel, and he actually died not that long afterwards. Showed, partly with Saxel, but I think just his name is on at least one of the papers, so let's credit him. The minimal generating set, the maximal size of an independent generating set for Sn is n minus 1. One direction of that proof is really easy. You've probably all seen the generating set for Sn that consists of swap 1 with 2, swap 2 with 3, swap 3 with 4, go all the way through. That's an n minus 1 element generating set, and if you pull anything out, you don't generate Sn anymore. The hard work is showing that you can't make anything bigger than that. Let me also mention there's papers by him and also by somebody with, I think, an Aachen connection, Sebastian Jambor, but I think he did this in, may have done some of this a bit later. So these papers appeared a long way apart, and I won't give you the things, but we do know, for example, that M of PSL2P is always either 3 or 4, and we know exactly when it's 3 and exactly when it's 4. So I think Whiston proved that it was always 3 or 4, and Jambor worked out exactly which was which. There's a lovely universal algebra result that Andrea recently taught me due to Tarski in 1975. So this might give something resembling a proof strategy for some of these, which says that rule K such that D of G is less than or equal to K is less than or equal to M of G, there exists an independent generating set for G of size K. And I've not yet looked at this because I only got told about it, I think, last week. So, but this is coming from universal algebra. This isn't coming from group theory, but it applies to groups. So, we know lots about D of G. We know very little about M of G. If you can find a single K where you can't find an independent generating set, then that's an upper bound on M of G because you've found a hole in the sequence just that there ought to be. I was going to put up a result we just proved, but I've run out of time, so I'm going to move on to the next section instead. So, Andrea's done a lot of things on this topic, as have other people. I'm not going to claim this is anything like a complete survey, but it's going to get some application in my next section. So, let me finish my talk and the week with something that links simple groups, graphs, generation and computation, and tell you an application. So this is section 5, and it's on product replacement. Okay, so our is we've got G given by K generators, and it's typically, you'll think of it as sitting inside GLDQ, but that doesn't actually matter here. It's just sitting inside some overgroup. I've been given some generators. Think matrices or permutations or whatever. We have good methods for permutations, so we use it mostly in matrix land. And the question you want to ask, so I said when I was working with normal subgroups, I could often make random elements of these normal subgroups. So a good question to ask me was, how on earth are you doing that? Well, here is one key step in how on earth might one do that. So how to make random elements of G. So if you were given Sn as an M cycle and a 2 cycle, you will probably quite quickly commit yourself to just sort of writing down short words in those is not getting you random permutations in Sn. You need something else. And here is a solution due to Lead and Green. Well, let's say, for a long time this was a very contested solution, but I think it is broadly now accepted as a solution. They say you want to pick, I've got till 12, right? Yeah. You want to pick an N that's at least as big as K. K is the number of generators you're given. And then you want to define, so this is an algorithm, you want to define an n tuple, x1 up to xn, and it's going to change as we go, but initially it's going to look like your k elements, and then pad it with as many ones as you need to make an n tuple. And I've written n in orange because it is undefined at this point. You just pick it somehow. And then, what do you do? What do you do? For t steps, and again, t is in orange because it is undefined. So, for t steps, choose entries I not equal to j in 1 up to n. So call one of them I and call a different one of them j. Randomly. So we're going to assume we can generate random numbers. And do one of the 4 following operations with equal probability. So what am I going to do? I've picked I and j, and I've got some n tuple, x1 up to xn, 4 things I'm allowed to do. And I'm going to write them 2 at a time. I can map it to x1, leave all of these alone, up to xi, and now post-multiply xi by xj to the plus or minus 1, and then leave all the rest of them alone. So you just hit xi on the left, right, by j inverse, or you can hit it on the other side. So xj to the plus or minus 1 times xi, leave it alone. So you multiply it on the left or the right by xj or xj inverse, and then after your t steps, you return a random xi. Now this caused a lot of mistakes. It's so simple, and it really seems to work. And so the question of how on earth do you analyse this to prove that it works was definitely a thing. But let me show you at least a lemma with a 0-line proof. If n is at least k plus 1, so provided I start with at least 1 spare entry, then I could just keep picking that entry as my xi, and I could build up any group element there that you like by multiplying out from there. And so I certainly can hit every group element, provided I start out with at least 1 spare slot. So n is at least k plus 1. That tells me that each g in G can occur. But like, are they equally likely to occur? They're certainly not independent once you start splitting these things out, because once you've spat one out, the next few are going to depend quite heavily on what was there when you spat one out. So Igor Pak did a lot of work on this, and he proved back in '99 that if n is at least d to the 1 over e, down there, E here is now the base of natural logarithms, which is not a number I use very often. I use it about as often as I use the Riemann-Zeta function. But E is the base of natural logarithms. So if you look at the number of random elements you've required to generate G with failure probability at most 1 over E, and you have at least that many slots in your product replacement algorithm, then product replacement tends to uniform as T tends to infinity. So provided you have at least that many slots, you will eventually start getting uniform random elements. Well, like, how fast? Because knowing that eventually I'm going to get something uniform isn't very helpful when I'm sat at my computer going, can I use this one yet? Is this one good enough? So, how quickly? Well, that's a very hot topic, so I'm not going to try and summarise it. It's a thing one can think about, let me say. Let me talk instead about this final bringing it together with a graph. Pack to find the product replacement graph. I think Pack defined it. Apologies if somebody else did and I just know it from him. In the obvious way, so you've got vertices to be generating n tuples, and you've got edges if you, let's say, generating n tuples x, because it's an n tuple of elements, and edges, you go from x is next to y if there's a product replacement move from x to y. X to y. Because
One of the 4 elementary ones.
one of those 4 elementary ones, so you multiply one entry on the left or on the right by one of the elements, or its inverse, one of these 4. So this is a nice 4-valent. Not always, there might be identities in some of the entries, at which point you stay where you are. Anyway, yeah, 4 times the number of places where there's stuff going on. So then Pack conjectured. So you can think of product replacement then as once you've picked your n, you're doing a random walk on this graph of length t and spitting out the vertex that you get to. For each time you're just like, okay, I'm going to walk along that edge, and now, okay, I'm going to walk along that edge. Pack conjectured, and this is still wide open in general, but so let's call this gamma k, gamma n of g, that gamma n of g is connected for all n greater than dg, and I should mention why this is significant, because lots of people, big name people, have been looking at this graph and trying to prove that it's an expander, for example, that when you get bits of it you get very fast expansion properties, and so you don't need to take very many steps to get to a uniform entry, but obviously that's only going to work in a particular connected component because you're stuck in the component that you started in. So we know that the components have, in many cases we know that the components have good expansion properties, but when is it actually connected? I'm hiding a lot of very deep work because I don't understand it well enough to tell you about it, but it's there if you want to look it up. So let me finish with another result of Scott's. So Gomez, Guralnick, and Harper, and this comes out of the stuff that Scott's just been telling us in 21, showed that if the spread of a group G is at least 2 or bigger than 2, at least 2, and my number of entries is strictly bigger than 2, so I'm not looking at generating pairs, I'm looking at least generating triples, then all non-minimal, tying in my last, no, non-independent, that's my word, non-independent, tying in the last section, generating, I'm going to have to clean a bit more board, generating n tuples of this graph. Generating n tuples form a connected component in gamma n of G. You're not going to be able to go from a independent n tuple to a non-independent one, but you can get from all of the non-independent ones to all of the other ones. So for example, if G is a finite simple group and you're taking at least 3 entries, then you can get from any, not one of these size ones, to any other, not one of those ones inside that connected component.
Are there questions? Yes?
You said you had another result on the independent generating sets. Could you tell twice?
Yeah, sure. So there's lots of stuff being done at the moment on independent generating sets, but I thought I'd mention something that I proved with Saul and Daniele because we just submitted it this week. So we were looking at the structure of independent generating sets, what elements can be in them. So this again ties into what Scott's done, and it's what things can appear in these minimal generating tuples. And there's an obvious obstruction to being in these things. So for a single element, X is in X for some, I'll drop the word generating, so for some independent X, there's a famous subgroup that controls being in a minimal generating set. So X is in some minimal generating set, independent generating set, if and only if X is not in the Fratini, and that's often the way that the Fratini is defined. Okay, so what about pairs of things? We know then exactly what elements could appear in independent generating sets somewhere, but what pairs of things? Well, here's an obvious obstruction. If X is in the thing generated by Y, or symmetrically, Y is in the cyclic subgroup generated by X, then the pair, and they're not equal to each other, then the pair XY is not contained in a minimal generating set. And Andrea and Daniele and Saul and I have just characterised all the groups where this is the unique obstruction to being in a minimal generating set. So I won't write down the detail, but in particular they're all super soluble and we've got a very precise description of what they look like. So sadly, this is too strong a property. It's not a good way to start studying these things. This is a beautiful, clear thing. This is what you might hope would be the next sort of obstruction, and no, it only gets you a tiny number of groups trying to rule out that, so there's huge amounts still to do. Thank you for the question.
Any questions? I actually wanted to ask also about this maximum of the whatever.
Yeah.
Is that, do we know, I mean, does the automorphism group of the group do something with these? If you
Yeah, you're going to send, you always send generating tuples to generating tuples, but you're not necessarily going to be transitive on them.
No, you're not. So you took 2 maximum ones, you won't, no.
I don't see any reason why you should be transitive on them now. Yeah. I mean, you're certainly not transitive on minimal ones, right? If we think about the fact that every edge, so many edges are there in the generating graph.
No, but on the back,
Yeah, so you can think of a lot of what Scott's been doing is looking at the structure of minimal generating sets and how many elements appear in lots of ones of size 2 for simple groups. And then this is starting to say, well, what can we say about the biggest ones? And we really know, in terms of explicit values, this is basically it. There's been some lovely work by Andrea and other people on soluble groups, but for the simples, we're at C.
Yes.
So, I may be missing something, but why does the result of Tim, Bob, and Scott not give a counterexample to Pax's conjecture?
I should have said on the...
it should be, the result is that they are contained in a connected component.
Oh, sorry. Did I say that? Sorry, I must have confused myself at that point. Let's correct that. Thank you, Scott. I contained them. It fixes that way. Sorry, I was just looking this up like 2 days ago, so I got all inspired to stick it in. So it could still be one giant connected thing, right?
And some related question, why does that lemma not imply that the conjecture is true? The lemma about each G...
Well, that's about a single entry, that's not about a tuple.
Okay.
Yeah, so one is every possible entry of G can appear somewhere.
Right.
That's very different from saying that the whole of G to the n is appearing in a connected component, say. And we don't want G to the n, we want generating tuples, but yeah.